Next, we are going to start exercises on number-theoretic functions. So this is the second one, and in this we are going to use something from the first exercise. As per the rule, we are not going to solve the odd numbered exercises, you already know. But in spite of that, because it's going to use result from exercise 1, so let us first see what exercise 1 tells us. So here you have two positive integers m and n whose factorizations are given, prime factorizations. And the primes that appear here, these pi's, p1, p2 up to pr, these are distinct primes, that also you know. And the exponents are, in both the cases, non-negative integers. It's not necessary, however, that all these primes pi appear in each of the factorizations, and that is why we are allowing the exponents to be 0. In general, they are non-negative integers. For example, say p1, the prime p1 actually divides m, then k1 will be a positive integer, but say p1 does not divide n, then j1 is equal to 0. So we have allowed that possibility, and in fact that is why we are able to write both m and n consistently like this using these primes. Anyway, so that's the setup. Then what this claims is that the GCD of m and n will then look like this: p1 to the power u1 times p2 to the power u2 up to pr to the power ur, where each ui is the minimum of ki and ji, minimum of the corresponding exponents that we have here in these factorizations. And the LCM of m and n is p1 to the power v1 times p2 to the power v2 up to pr to the power vr, where this time each vi is the maximum of ki and ji. It's not very difficult to prove this, and in fact we have proved it. It is one of the exercises in Herstein's topics in algebra. In the third section of the first chapter, we have this exercise and we have solved it there. So if you want, you can go and check it there. But anyway, today we are going to only use it to calculate this GCD and this LCM of these two numbers. One of them is 12,378 and the other one is 3054. So that means first of all we have to express these numbers like this. And then of course we know what to do to find the GCD and LCM. So let's see the solution. So the solution starts like this. The factorization of 12,378 as a product of primes is this, where we have deliberately written these exponents, which normally we won't write because we want to really use that result in exercise 1 carefully. So we have written 2 to the power 1 times 3 to the power 1 times 509 to the power 0. This is a prime. Okay. At the end of the book, there is a long list of primes. You can go and check there. This to the power 0, which means that this 509 actually does not divide this. However, to maintain consistency and to create the situation of exercise 1, we have decided to include 509 in the prime factorization of this number. Normally we won't do that, okay. And then 2063, this is also a prime to the power 1. It turns out that this product is equal to this. Similarly, the prime factorization of 3054 is 2 to the power 1 times 3 to the power 1 times 509 to the power 1. So now you see the reason for including 509 here. There are of course other primes. For example, 17 is a prime which actually does not divide this or this. So there is no need to include that. Times 2063 to the power 0. This prime, although it divides this, it does not divide this. So now we know what to do to write the GCD and LCM. So the GCD will be this, where now you know that the exponents have to be taken like that. That is, each exponent will be the minimum of the corresponding exponents of the prime powers of that prime. So, for example, if your prime is 2, here both the exponents are 1 and the minimum of 1 and 1 is 1, so you have 1 here. Here also you have 1 and 1 and the minimum is 1, so you have 1 here. For 509, however, the exponents are 0 and 1 and the minimum is 0, so we put 0 here. Similarly, here the minimum is 0. So these primes actually do not arise in the GCD, and the GCD turns out to be 6. And next we go for LCM. To calculate the LCM, this time the exponents will be the maximum values of the corresponding exponents. The maximum of 1 and 1 is 1. Maximum of 1 and 1 is 1. Maximum of 0 and 1 is 1. So this time it will be 1. Similarly, maximum of 1 and 0 is 1. So this is the LCM. You may at once think that this is a very fast way of calculating GCD and LCM. Normally, how do you calculate the GCD of two integers? You apply the Euclidean algorithm again and again, or the division algorithm. Or you can apply, that itself is called the Euclidean algorithm. You keep on dividing. First you divide one integer by the other, then you get a quotient and remainder. If it's a complete division, then there itself you are getting GCD. Otherwise you get a non-zero remainder. Then you divide the divisor by the remainder, and then this process goes on until you get full division, which is guaranteed after a finite number of steps. It takes a long time to find the GCD that way. This, however, seems almost like we are instantly finding it. However, do not forget that we have to be able to factorize the given numbers, which itself actually is a very, very difficult task. Not only should you know the primes that divide this, but you should know the primes. We don't know all the primes. So anyway, it's a very difficult and time consuming task. So for small numbers like this, it works well, but for large numbers, in fact here itself you can see that this really goes beyond your capability to simply write a factorization. Most of us don't actually know these numbers as primes, although the first few we know, say 2, 3, 5, 7, 11, 13, these things that we know. However, these ones we don't really know. Okay, so it takes time to factorize a number. But anyway, let's see the next one. The next one is this fourth one. The third one, of course, is left to you. And again we go back to exercise 1. In the notation of exercise 1, you have to show that the GCD of those two positive integers, m and n, is 1. That means they are relatively prime if and only if the product of those corresponding exponents, ki, ji, is equal to 0 for all I. So let's prove this. So this is one half of the solution. In this half, we assume that the given numbers are relatively prime. Their GCD is 1. What does that mean? It means that they cannot have common prime factors. But their prime factorizations were already given. The one for m is p1 to the power k1 times p2 to the power k2 all the way up to pr to the power kr. And for n it's p1 to the power j1 times p2 to the power j2 all the way up to pr to the power jr. So this means that if you choose any prime, say pi, then the exponent of pi in the factorization of m is ki, and the exponent of that same pi in the factorization of n is ji. If both of them are non-zero, that means pi divides both of them, but that should not happen if this is true, which means that both of them cannot be simultaneously non-zero. So at least one of them has to be equal to 0. So for each I, either ki is 0 or ji is 0. But then no matter what the case is, ki gi will be equal to 0. And that is one half of our claim. Now let's prove the converse. Conversely, let ki ji be 0 for all I. Then I forgot to write that one more line will be there. Then either ki is 0 or ji is 0, because then only the product will be 0. If both are non-zero, then the product is non-zero. And that is why the minimum of ki and ji will be equal to 0 for all I. But we already know from exercise 1 what the GCD of m and n is. It is this. Now each minimum is 0, so you are getting 1, and that is why m and n are relatively prime if this condition is true for all I. That's the solution. Let us see one more. Next we have 6. For any positive integer n, we have to establish this inequality. The number of positive divisors of n, tau of n, is at most 2 times square root of n. So let's see the solution. So this is how we start the solution. Let's see what the solution says. For any positive divisor d1 of n, n will have positive divisors. At least one positive divisor is there, which is 1, but there may be many others. For any such positive divisor d1 of n, there exists a unique positive divisor d2 of n, another one, not necessarily different from d1, just saying that for d1, another positive divisor d2 of n exists which is unique, such that their product is n. In other words, this d2 is just n divided by d1. For example, if you have the number 12, say, think of 12 in place of n. If your d1 is 1, then d2 is 12. If your d1 is 2, d2 is 6. If your d1 is 3, d2 is 4, like that. If d1 is 4, d2 is 3. Okay, so that way also it goes. Now, of course, in general, one of them will be less than or equal to the other. They may be equal also. So we have kept that possibility alive, that d1 may be equal to d2. So let's assume without loss of generality that d1 is less than or equal to d2. Now if you multiply both sides of this inequality by d1, the inequality won't change direction, because d1 after all is the positive integer. Then we will have d1 square less than or equal to d1 d2. But d1 d2 is n, and from this you get this inequality that d1 is less than or equal to square root of n. Instead, if you multiply both sides by d2, then you get d1 d2 less than or equal to d2 square, or n less than or equal to d2 square, or square root of n less than or equal to d2. So you have uncovered the fact that n has a positive integer, or this is how, I mean, not positive integer, I wanted to say positive divisor. Let me phrase it this way. Whenever you write n as a product of two positive divisors, one of them is less than or equal to square root of n, and the other one is greater than or equal to square root of n. Regardless of what this d1 and d2 are, that is always the case, depending on which one is greater and which one is smaller. Now we are going to use this information to next say something. Okay, so before we can use this observation, let's just write it down like this. So when we factorize n as a product of two positive integers d1 d2, one of them is less than or equal to root n, like this d1, and the other is greater than or equal to root n, like this d2. Now we divide the situation itself into two different parts. depending on whether our original n is or is not a perfect square, you will see why this is needed. Say n is a perfect square, then we are saying then the number of such pairs is tau of n minus 1 divided by 2 plus 1, which equals this. But you say, hold on, what is happening suddenly? Pairs means what pairs? Pairs of those two numbers, d1 and d2. Okay, if n is the perfect square, then the number of such pairs is this. How exactly? Let's take one example to understand better. Say n is 16, then the positive 16 is a perfect square, 4 square. Then the positive divisors of n are these. Tau of 16 is 5, you can calculate. And actually you can see the positive divisors. There are 5 divisors, 1, 2, 4, 8 and 16. So in this case, if you find that pair of numbers, d1, d2, then one pair is 1 and 16, the other pair is 2, 8, and there is one more pair, 4, 4. You see that here d1 and d2 are equal. That is because 16 is a perfect square. That is why we have to handle this case separately. The other case where n is not a perfect square is a little different and actually easier to understand. But anyway, let's see what is going on here. We have carefully written 1 here and 16 here because in our previous analysis, in the previous part of the solution, d1 was the number which turned out to be less than or equal to root n. Okay, so we want to keep that intact. So 1, 16, 2, 8 and 4, 4. Alright, now where does tau of n come into this in this picture? Tau of n is the number of positive divisors, which in this case is 5. Now, apart from this 4, which is in a sense alone here, it's like it has no one else to pair up with. The others have got partners and together they are producing n. 1 and 16, 2 and 8. So if you are using these divisors to create 16 in the form of these pairs, you would take 1 and 16 together, so 2 numbers are gone. You will then take 2 and 8 together, 2 more numbers are gone, and you will be left with only one number, that is 4, which has to make do with itself only. It has no one else. So that means, how many such pairs are you getting? That is the question. So if you momentarily forget about this 4, let's just leave this 4 out. Then you are having these other numbers which you can use to create pairs. The moment you leave 4 out, the number of available numbers becomes tau n minus 1. And then when you create pairs, the number of pairs will be 1/2 of the available numbers because you are creating pairs. So that is why divided by 2. However, plus 1 because that lone number creates its own pair. So that way you get this many such pairs. Alright. So now there is no confusion about this line at least. We still don't know where all these things are going, but let's just go with the flow and see where it leads us. Next we consider that other case where n is not a perfect square, and in this case the number of such pairs is simply tau of n divided by 2. And to clarify that, we have this example. Say n is 12, then these are the positive divisors of 12, 1, 2, 3, 4, 6 and 12. In this case those pairs are 1, 12, 2, 6 and 3, 4. Okay, so you can see that we have just simply paired up all the numbers, and that way we have got the pairs. So the number of pairs is 1/2 of the number of available numbers, which is tau of n. So tau of n divided by 2 such pairs will be there in this case. If you are still finding it a little confusing as to how this case is a slightly different one, you just see, you think for yourself, n is a perfect square here, so it's the square of something. In this case it's 4, but in general I am saying it's the square of say d. Then obviously d comma d will be one pair because of the way we created those pairs. One of them will be d comma d. So that can be handled a little separately like this, and in these two cases we have got these two numbers. So in general, the number of such pairs is either tau of n plus 1 divided by 2 or tau of n divided by 2. Now what are we going to do with these pairs? Note that each such pair contains a divisor that is less than or equal to square root of n, and that divisor is d1, and all such divisors has been accounted for in these pairs. So by creating these pairs, essentially we are neglecting the d2s, because next we are going to talk about these d1s only. Let's see how. Now before we do anything else, we uniformly write our observation like this. If x is the number of positive divisors like d1, that is those divisors which are less than or equal to square root of n, then x is tau of n plus 1 divided by 2 if n is a perfect square. Otherwise, if n is not a perfect square, then that number is tau of n divided by 2. And now we are going to somehow link this with, let's see what we do next. Next, let us observe this somewhat peculiar but very easy to understand condition on x. What is x? X is the number of positive divisors of n which are all less than or equal to root n. So does that not imply that x itself is less than or equal to root n? At once it seems a little confusing, but why? Well, the number of positive divisors which are divisors of n and less than or equal to root n. Now how many numbers are there less than or equal to root n? Obviously that number itself will be less than or equal to root n. That cannot exceed root n, and that is why x is less than or equal to root n. And that means that depending on what the case is, either you have this or this. Now note that even when you have this is a little greater than tau of n divided by 2. By how much? By 1 over 2. So even in this case, this quantity is still less than or equal to root n. So in general, this is less than or equal to root n, or tau of n is less than or equal to 2 root n. So that's how you have this inequality established. So let's just end this video here itself, and there are of course many other exercises that we will see in the next number theory video, that means next week. So see you next week with more exercises. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.